When we left Lest Our Intrepid Heroes yesterday, what were we discussing? Energy. Specifically, work. And what is work? We better have been. What is work? It is the method by which you change energy. I spent this whole ad nauseum time yesterday doing this whole spiel about, I was really just flexing my energy. No, that would be weird. Okay, interesting point. Okay, about us not knowing what the heck energy actually is, and the answer is essentially work. Energy is either work in action or the ability to do work. The other day, I think somebody said potential energy. And there you go, Colin said potential energy. And I asked Colin, well, the potential to do what? And the answer, as always, is everything in energy revolves around this guy right here. Potential energy is the ability to do work. Okay? Or, in other words, potential, it's a little bit weird of a sentence, because what I just said, kind of breaking that all down, is what's potential energy? The potential to do work. AKA, potential energy is the potential to change its energy. Which is, I know, a strange sentence. Ultimately, everything revolves around this. Okay? If you consume energy, what you are consuming is something that has the ability to do this. If you are spending energy, like let me show you right now. Here is me spending energy by lifting my arm up and down. Do you think I'm spending as much energy when I let my hand drop down? Why not? Well, why am I not spending energy myself to let my hand fall down? It's probably just gravity that's doing the work, right? It's gravity that's pulling it down. Versus if this, which way are my muscles pushing? Up. And which way is it going? Up. AKA, we have our three things that are necessary for work. What are the three things necessary for work? Force. I mentioned this yesterday. As a matter of fact, probably a better way to say work as opposed to there's three things necessary is it's kind of force is almost like a, yeah, you kind of expected that, given that, sure, whatever. Okay, given that force is the ability to move something. So probably a better way to say this is work is when force does these other two things, okay? So I gave instances where this does not exist. Well, actually, let me finish this first. What's the second thing you need? Displacement. And again, we mentioned this yesterday. Apologies for people online. I'm doing a demo in front here. You're not going to be able to see it, but I will describe it. I'm going to push a tennis ball across the table, okay? I'm going to block my hand right here, okay? And I'm going to push it so that my hand stops right there. Is the displacement the ball going from here all the way over here? No. The displacement is the displacement while the force was in action, okay? So if I'm talking about my hand, the displacement was from here to where it stopped. If I was talking about friction, though, then what would the displacement be? Where would I start the displacement? Where the hand started, all the way over here. Why would the displacement be different for friction?
Because friction is on it the entire time.
Friction's on it the entire time as opposed to my hand in that case. Cool? So in other words, another example I gave is throwing the tennis ball across the room and hitting the wall. All right? Is the entire path of the tennis ball the displacement for me putting in energy? Absolutely not. It is the total displacement if I want to talk about gravity. Okay? All right. Finally, what's the third thing necessary for work? They have to go the exact same direction. Now, this has weirded people out in the past. If I take a ball and I roll it across the table, you mean force of gravity isn't on? No. We are not saying force is zero in this case. We're not saying that force is doing absolutely nothing. What we're saying is, yes, gravity is pulling on this, but is gravity currently affecting the motion of the ball? No. Okay? Now, you could correlate that and you go like, well, gravity is affecting normal and normal is affecting friction, and you were not wrong, but the force we would analyze there would be friction, because the friction is the one parallel to the ball in that particular case. Okay. I then gave three different examples yesterday. I just did one of them just a second ago of when these things are off. So like if I take this tennis ball and I throw a tennis ball in space, as I'm throwing it, am I doing work on it? As I'm in the process of doing it, I have a force, it's going some displacement, so yes. After I am done pushing on it, Am I doing work on it?
No.
No. Okay, and so actually, is any work being done on the ball while it goes through space? Because there's no force. This isn't here. You cannot have work without any of these things missing in this particular case. So yes, so there's no force on that, so there is no work. Also, what you should be able to notice is what is true of the motion of the ball that clues you into the fact that energy of the ball is not changing. How is the ball traveling once I let go of it in space? Same speed. Actually, let's change that a little bit slightly. Same velocity. Yes, there's a major difference that's coming, especially between the two of those in next semester that I want to make sure and kind of make sure to continue to highlight that. Next, number 2, am I putting a force on this table? Yes, absolutely. Am I doing work to the table? No, I am not doing work to the table. What's the reason up here that I am not doing work to the table? There's no displacement. Correct. What clue could you look at the table very easily see to let you know, even if you didn't look at this, that absolutely I wasn't doing work to the table? It wasn't moving, and it stayed not moving the entire time. Okay. Finally, is there a force of gravity on this ball? Yes. Is the ball going through some displacement while gravity is on? Yes. But is gravity doing any work here? Because they are not going the same direction. All 3 must be present in order for work to occur. Okay. Then what we ended with is we talked about a couple of examples here. Hey, if a ball goes a displacement this particular way and a force goes that way, that's positive work. Terrible handwriting on this thing. But in other words, when I say positive work, that means positive change in energy, aka you're putting energy into the object. If I have an object going this way and force goes the other way, that's negative work. Again, aka what we're saying there is that's a negative change in energy, or you're taking energy out of the situation. And finally, this is that last example. If the ball is going this way but a force is down, that is 0 work, aka there is no energy being changed in that particular case. Your gloves? Grant has them. I told him to leave him here. He said he would see you later. All right. Next, off of the back of that whole conversation, conceptually, the very end of the hour, I gave you an equation for work. What is it? Actually, I gave you 2 equations for work. Let's start with the easier one. Force parallel to displacement. This will manifest itself in very nice ways a little bit later on. Okay. Right now, it looks like a very easy simplification to the other equation, and it seems like it's not necessary whatsoever. I will guarantee you this one will be really nice as we continue, like especially tomorrow. But what was the other equation for work? And essentially, what you'll notice is missing off of this and is not here is what I'm saying is that this takes place when they don't point the exact same direction, okay? And what this cosine is doing is making sure that they are parallel in that particular case. Let me give you about 3 instances where that's the case. So let's say, for example, here's a ball. The ball is going to roll across the table this way, and someone's, I don't know, pulling the ball with a string or a yo-yo or something. Here's the force, and that's 30 degrees. What angle should we use for this equation? 30 degrees is correct. Now, I highlight this because, be wary of this, angle is always measured. It's actually over there on the right side of the board already, right over there, between displacement and force. As a matter of fact, every force in a force diagram has its own possibility for work. So every force has its own angle. The only thing that's going to stay consistent is displacement, meaning angles will not start at your standard 0. They're going to start from wherever the heck the displacement is. So in this example that we used a second ago, displacement is to the right, the force is up the hill, and thus the angle is 30 degrees. But let's choose one that's a little bit more complicated, still not that bad. Let's say instead of a ball rolling across the ground, I start pushing a book up a wall. Okay, so now I've got a book on a wall, and I'm not pushing straight, I'm not pushing up, I'm horizontal, I'm pushing once again at 30 degrees to the horizontal. Now, I did say specifically the book is going up the wall. What angle should you use here? Should be 60. Why should it be 60 in this particular case? Well, once again, here we go. If this, let me use pink for my displacement here. If displacement is up the wall, angle, even though this one's given to me, must be from the displacement to the force. Okay? Of course, horizontal to vertical, what's that angle? You got this. 90. So if that's 30, what's the leftover bit got to be? 60. All right, now let's do the most complicated one today. Most complicated one today is this. Now we're going to use 30 degrees again. The ball is rolling down a hill. And specifically, I'm going to focus on gravity. Which way does gravity go? Down. Oh, sorry. Make sure I'm consistent with my... This is displacement. Gravity is down. Discuss quickly in your group what angle should you be using. And more importantly, why.
I was here to turn around. I think
It's giving me vibes.
however, so listen up. Yeah. Oh, so we also. Yeah. Okay.
All right. What you got?
Are you kidding me, Spino? Is it 60?
It's 60. All right. Here's how you can more easily do this. What's your ideas on why it's 60? How many of you got 60? Okay. Here's what you need to do. Number one, did all of you see that it needs to be this angle here?
Yeah.
Okay. So then, of course, the question is, what is that angle there? One of the things I highlighted last chapter is that all angles in this, as complicated as it gets, you can kind of simplify it by going, it's either with the horizontal or it's with the vertical, right? Or, let's do this a little bit more geometrically. This angle has to also be that angle, yes? So, horizontal, what does this have to be? 30. And if that's 30, then the other one has to be 60. And again, you can even shortcut this a little further by noticing that one's with the horizontal and that one's with the vertical. So it's the complementary right there. Okay? That is one way that you can do that pretty easily. All right. We're going to practice with this a lot more in a minute. I think we did this yesterday, but I know I have a handful of people that weren't here yesterday. So let's remind ourselves of this real quick. What are the units for force? Newtons, correct. What are the units for displacement? What are the units for a cosine? Bravo, no, not a cosine. There are none, correct. Remember, a cosine basically spits out a ratio. If it spits out a 1, essentially what that means is 100%. 100% of them are going the same way. If it spits out a 0, none of them are going the same way. But there are no units on that ratio. Even when you guys did trig last chapter, if I said, hey, blah, blah, this is 5 meters, this is 3 meters, this is 4 meters, here's the angle, what's the cosine of that angle? What is the cosine of that angle? 4/5 or 80% or 0.8. Yeah, why didn't I put the meters up there? They cancel. The units are always going to cancel because it's a ratio. Ratios always cancel the same units on top and bottom. He's been going a while. Yeah, probably just not going to work anyway. All right, moving on. Units on this, newtons, meters, and nothing. So technically, what are the units for work? A newton meter. That's why I say technically. You're skipping ahead of me, but it's completely fine. Ultimately, what I tried to remind you of that was this. This is the equation for Newton's second law. So what are technically the units for force? What are the units for force technically? Well, what are the units for mass? Kilogram. And what are the units for acceleration? So the units for force are technically a kilogram times meter over second squared. And what that means, like I said yesterday, was if I take this 1 kilogram right here, and I'm sitting in the middle of space. And the reason I go to space is so that there are no other forces other than me. And I put a force on this, and I put some force, whatever force it is, that causes 1 kilogram to accelerate at 1 meter per second squared is defined as 1 Newton. That's what a Newton is, by definition. If I do that thing with a Newton, I push it so that at 1 kilogram accelerates at 1 meter per second squared, and I do that for a meter, the energy that I would put in from that 1 Newton pushing at 1 meter per second squared is going to be 1 joule. 1 joule. Simply put, your energy needs to be in joules, and that correlates directly to how many newtons and how many meters in that particular case. Questions, concerns? So what's energy?
Is work in action.
Not bad, okay? Energy is the ability to put out work, or like you said, kind of work in action, something going through it. Or here's another way to put this. When an object does what we expect it to do, energy is spent when it does what we expect it to do. If I take a ball and I drop it, what do you expect it to do?
Fall.
You expect it to fall. So, in that case, would work be positive, negative, or zero? It'd be positive. How come? To go in the same way, which once again cycles back to the other thing I wanted to talk to you about is this: is energy is a scalar. What does that mean to you?
No direction.
Energy by itself does not care about direction, to which any eagle-eyed student looks at this diagram right here that we did and go, yes, you did care about direction. And says, yeah, I hear you, but actually, no, I don't, because in this case right here, where the ball goes to the right, we get positive energy because it does what we expect it to do. If I had a situation like, let's go down here. Here, does gravity put any energy in? No, because it doesn't do what we expect it to do because of that force. It doesn't go the wrong way, it doesn't go the right way, it doesn't do anything. Versus, finally, if the ball is going down and has a force of gravity down, we would consider that work positive. Does positive work care whether or not the ball is going right or whether or not the ball is going down? No, direction doesn't matter. What matters, sort of with direction, is that they are going the same way. Does that make sense? Okay. Now what we're going to do is I'm going to give you a handful of examples that you're going to see in the homework, the stuff, so that you can kind of try to get a feel of how all of this stuff gets put together. I got 3 examples to try to get through it relatively quick and accurately. I'm going to make some simplifications for us here, and they are as follows. Today we're just going to look at a box. We're going to say every time I push the box, force of person on box, I'm going to push with 100 newtons. Okay? Roughly speaking, about a little more than 22 pounds, 23 pounds-ish of force. We're going to say the box weighs 125 newtons. Both of these two would be relatively easy to control. Well, this next one would not be, but again, we want to try to keep things as simple as possible. Let's assume that friction is going to stay at 25 newtons. Now, for all 3 of these examples, that probably wouldn't take place. But again, we want to keep it relatively simple. And like I said, we're going to look at 3 different scenarios. Here's the first one. I have a box sitting on the ground, and we are going to pull on this box, kind of think with like a string or something like that, at an upward angle of 60 degrees. Try to highlight that in a different color here. 60 degrees. Even though I'm pulling upward at an angle of 60 degrees, you will notice my force is over here. Notice that gravity is way bigger than the force, well, not way bigger, but it's bigger than the force I'm pulling upward. So what do we expect this box to probably do? Probably slide along the surface, yes. Now, I am going to draw the displacement. Okay, long term in here, I would expect you to slowly walk away from not drawing the displacement. Displacements don't go on force diagrams. But it will, at the very beginning, give you a much better idea of what angles are. So if you want to maybe do it to start off with, okay, make sure that you draw it separate. And again, don't do this long term. Now, our goal now is to find the work done by every force. This equation right over here, the main one we're going to use today, this guy right here, that is not the total work done on an object. As a matter of fact, I demonstrated this for you yesterday when I walked across the front of the room at a constant velocity. What is my force diagram as I walk across the room at a constant velocity? Gravity, normal, friction, muscles. Cool. All right. Are all 4 of those doing work? No. Which 2 are not doing work? Gravity and normal, because there's no, not quite. Not because I'm did some. Not right now, but I was. That's probably not the best way to put it. Okay, that's not wrong, but actually I think there's a better way to say that. Displacement, this way. The force is related half. Perpendicular.
No work.
So they are not going the same direction, kind of what you were saying, but I think it's more easily justified by talking about it in terms of the force and displacement don't point in the same direction. All right. So again, our goal right now is to find the work of every force. So how should I probably begin? Oh, close before that actually. Force diagram. Correct. All right. Help me out. What's the rest of the force diagram? Let's go in yellow. Gravity. I'm going to wait on normal for a second. Friction, which way? Now, you are right, because I did say a rope. It's probably tension, but for the sake of argument, given what I said just a moment ago, we're just going to call this person on box. But that is, if you want to use tension, it just means that tension's 100 newtons. Okay, the reason I waited on normal, of course, is should normal be greater or equal less than force of gravity? Less, because tension's pulling up. Essentially, once again, this is just this. If you ever struggle with some of these questions, just think of it in real life. If I lift this guy even a little bit, even if it doesn't leave the table, does force normal get smaller? Which you know, because friction also gets smaller when you do that. And of course, vice versa. Push it down into the table, does force normal get bigger? Yes, friction also gets bigger, blah, blah, blah. All right, here we go. By the way, once again, these numbers will stay exactly the same the entire time. Now, one number that you're going to need, which I purposely avoided a second ago, was displacement. You're going to need to know what displacement is. The reason I waited on displacement is I just want to, as I walk across the front of the room, my muscles are putting in work. Yes? Positive, negative, 0. My muscles, positive, negative, 0 work. Why? You know, changing direction now. Pushing the way it goes 100%. Okay? Is my total work increasing? Staying at constant velocity. So why I'm putting energy in, why is the total not increasing? Because another force is taking energy out. What force is taking energy out of me? Friction in this particular case. Now, as I was doing that, my displacement was continually going up. Displacement in a lot of these examples is technically arbitrary. By arbitrary, I mean, okay, if I pick 2 meters, I'm going to get a certain amount of energy. Guess what happens to that energy if I double the displacement? It doubles, right? As I walk across the front of the room, if you want to calculate the work that Spainhour is doing, you can't really do that until I stop, right? Because you don't have like an overall. Technically, if we had like a ticker tape up here, how much energy Spainhour is using, as I continuously walk across the front of the room, what's that number doing? It's changing. It's like we can't get an answer to it until we pick a particular displacement. Meaning, displacement is arguably arbitrary, because if you pick 2 meters, you pick 4 meters, well, obviously the 4 meters is going to be twice as much because they're going further. That kind of makes sense-ish a little bit. All right. As opposed to some of these other numbers that are definitely changing the scenario a lot more. So that being said, you pick the displacement. 3 meters it is. All right, here we go. How do I calculate the work of person on box? Well, my equation is, watch carefully, force of person on box times displacement times the cosine theta of person on box. Why did I put subscripts on both the force and the angle, but not on the displacement? Correct. And then, of course, for the other two, they are different between all the different works. And that's there to remind you of that. Okay, let's start with the easy stuff first. What is the force of person on box based on what I've already told you? 100 newtons. Okay, you just decided a second ago, what's the displacement? 3 meters it is. What should the angle be? Cosine of 60 is correct. Now, real quick, because this will help you a ton with how often it's used throughout this chapter, let me just do this for you real quick. Here's your basic triangle, your 60, 30, 90, or 30, 60, 90, depending on how you want to draw it, 2 root 3. Okay, one that's really helpful to know, you don't have to, you can punch in your calculator every time. What is the sine of 30 degrees? There's 30, so sine of 30 is? Sine is what? 1/2, correct. It's always, they use sine of 30 so freaking often that you can save your life a little bit, like a little bit of time not punching it in every single time. If you remember that, you certainly can punch it in every time. By that same extension, what's the cosine of 60? Also 1/2. Yes, the complementary sine and cosines are in fact the exact same amount. So I got 100 times 3, 300 times cosine of 60, so my overall energy is 150 what? Nope. Joules. Well, we're going to do the right unit because it's work and not force. All right, now, moving on. Let's go to an easy one here real quick. Let's do the work of normal. Now, you might say, Spainor, work of normal is not easy because I got to find force of normal and displacement should be exactly the same thing. Okay, if you were to find force normal, how would you have to do that? Yeah, and that stuff's not going away. You're absolutely going to be summing forces in this chapter. It's 100% going to stick around. As a matter of fact, more so than anything I have ever said in this class is going to stick around. Summing the forces is going to stick around. Physics 2 had their, I think, 9th test of the semester today, and that 2 of the problems, that's the fundamental thing that was the basis of everything they were doing, was summing the forces. So, that being said, I could sum the forces to find force normal, but here is a quick trick. Yes, I don't know what this is. I know that's 3, but what's the angle? 90. What is the cosine of 90 degrees? 0. Or in other words, these are perpendicular to each other. How much work is this going to do? So here's the work that I would show. Okay, I would not put the large equation up there. I would in fact just shortcut that to say, hey, work of normal is 0 joules. But I do want you to back up your reasoning, and here's the easy way to do that. Work of normal is 0 joules because force of normal is perpendicular to displacement. By that extension, what other work is going to be easy to calculate? Gravity. I'm going to write it up there, same reason. Now, we talked about this yesterday, but again, I know there was a handful that weren't here yesterday, and it's good review even if not. What angle would you use for gravity? 90, correct. You do not have to use 270. You don't need to use any angle whatsoever that is outside of 180 degrees. And the reason why is this. Quick aside over here. Let's remind ourselves of what cosine actually is. If this is some magnitude r at 0 degrees, what cosine does is figure out how much of that's on the x, right? So at 0 degrees, you should get a 1 because 100% of it's on the x. At 90 degrees, how much of it's on the x? None of it. Sure, that's why perpendicular, none of it's over there. Okay, at 180 degrees, how much of it's on the x? All of it, but it's going the opposite direction in that particular case. Now, watch here. 270, how much of it's on the x? Is that the exact same thing as 90? And more importantly, watch this. If I go 30 degrees or I go negative 30 degrees, or if you want 330 degrees, does that change how much is on the x? Both of these have the exact same component on the x. One thing I did forget to mention yesterday, I'm going to go back real quick and cover this real quick. Okay, in this equation, this most important equation that I highlighted here in blue, whenever you use this, these two are never negative. They are just magnitudes. I don't care if they're up, down, left, right, whatever. They are always, 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 always positive. What will make your works negative is this guy. The angle will always make it negative. If you try to make these negative and then do this correctly, then you're going to end up canceling negatives that aren't supposed to cancel. And yeah, those two are always positive. That is going to be what makes it negative. And you see this here. If your angle is between 0 degrees and 90 degrees, you're going to get a positive answer. Why? Because the force is pushing the same way as the displacement. Maybe not as much, but it's still pointing the same way. Once the angle goes to 90 to 180, now it's pushing against. The force is opposite of the displacement, and so it should be taking energy out in that particular case. How are we doing? Cool beans. Let's go back to our regularly scheduled programming. We have one more to do. We need to find the work of friction. Work of friction is equal to force of friction times displacement times cosine theta of friction. What's the force of friction? 25 newtons. What did we say displacement was? 3 meters. And what is the angle for friction? 180 degrees. Remember, your angle is always measured from the displacement to the force. That's why it's 180. Also, quick trick on this as well. Coming back down here real quick. I don't want to write cosine of 180 a whole ton, and I imagine you don't either when you already know what the right answer is, and that's a bunch of extra work. You don't have to write a bunch of extra work on physics. So here's what you do. What is the cosine of 180? Almost. Very important to say negative 1 on that particular case. You've noticed me simplify a lot in here when we cancel stuff, like in this equation. We did this a ton, where I point this up to 0 a bunch. You can use that in this way as well. Rather than rewrite this, I'm going to put this arrow to negative 1. So I got a negative 1 right here, and the work that friction is doing is how much? Does it make sense that that friction's taking energy out of the situation? All right. Now, let's look at our overall answers here. And now you should be able to answer a question based on energy, but I'll also relate it to forces. Should this box be speeding up, staying the same velocity, or slowing down based on what we just calculated?
Speeding.
Why? Agreed. Why?
Because the work of the person on box is greater than the work of friction.
I'm going to say that a little bit differently, but yes. Okay. Because you're putting more energy in than you're taking out. You're putting more energy in, okay? It's kind of the situation I talked about where I was walking around at constant velocity. What is my total work net when I walk around like this? I don't know, what's my work net? What's the total work? We add up all the works that are happening to me. What is the total? Should be 0, because my energy is not changing in total. Now, am I putting energy in? Yes, but so why is it 0? Friction's taking the exact same amount out. So if I put 200 joules in, friction takes out 200 joules, my overall change is 0, and so energy doesn't change. Now, that is different when I take off. Because when I take off, my force forward has to be greater, and therefore I put more energy in than I'm taking out in this way. Or, in this case, connecting this back to last chapter, here's why that works. Which way would this accelerate if we went back to last chapter? Which way would this accelerate? In the x, right? You know it's going, in the positive x. You know it's going to speed up. We just saw that a second ago. AKA, how would we do that? Well, I would find the force in the x, and I would do that with trig. I would write force tension, force person on box, 100 times the cosine of 60, which we already said is 1/2. So that would be 50 newtons forward. Well, how much force is pushing back? 25. So is there a net force that way? So do you expect it to speed up? Now, I gave you two explanations there. Please understand that I did both because I need both. The second one was the forces example, which you're probably more comfortable with, and that's why people usually side with that explanation. But I do need you to talk about it in terms of energy. The original energy explanation is I'm putting more energy in than I'm taking out, and therefore the object is speeding up. Questions, concerns about that? All right, we're going to use, again, all the exact same numbers, but let's change the situation. I'm going to use the exact same box. I'm going to use the exact same force. This is force of person on box. It's still going to be at 60 degrees. The only difference is rather than push it along the ground, I'm going to push it along the wall. We are also going to assume that through some means, whatever, that this box is currently going up the wall. So again, if you need a real world analogy here, that is this situation right here. Here's the box, the book on the wall, and it's this pushing a book directly up the wall like that. Does that make sense? Although it's a box, it's also a 40-pound box, so probably not easy to do. All right, question once again is exactly the same. What are all of the works going on here? You will notice that some of them will change and some of them won't. But how should I probably begin? Force diagram. All right. What is my force diagram here? Gravity down. Ooh, to the left. Agreed. Force normal is to the left. Of course, we got force of person on box right here. I did draw it a little bit bigger than gravity. And friction should go down. Why is friction pointing down? That's correct. That's not going to help you as much on the test. It's opposite of direction of motion. The main reason I highlight that is that last hour, a lot of students incorrectly thought, oh, it's the opposite of the way you're pushing. No, it's not. It doesn't go the opposite of the way you're pushing, because if I was pushing up, the box was sliding down the hill, which way would friction go? Back up the hill in that particular case. All right. Now, the great thing about how we just did this is all I'm going to do is I'm going to switch colors to pink, and we're just going to ask, does it change? If it doesn't change, we can leave it alone. Does the work of person on box change? Well, let's see. Does the force change? No. We're going to use the exact same displacement, so does the displacement change? No. Does the angle change? Yes. Because remember, angle needs to be what in this case? Which way is the displacement? Again, I don't like to draw this, but it can help. Here's your displacement. So what does your angle need to be? 30 is correct. All right. 30, if I'm not mistaken, is about 0.86. So that should be 86 3 times 240, 250 and change. What do you got? I'm going to need your help on this. I don't have that one off the top of my head. You can do it. Remember, anytime we do stuff like this, I expect everybody to be calculating. 289, let's just go 260 now. All right, does it make sense that the push that I did in this case spends more energy than the previous one? Why? Agreed.
Because of more forces going down, or sorry, against your force.
I'm going to say that a little bit differently, but I think you got it. Okay, more forces in the same direction.
Yeah.
At 60 degrees, there was less. It was half. Here, it's 86% is going the same way, so we should get more work out. All right, next. Does work normal need to change?
No.
Wait a minute. Work normal, I agree with you. Work normal pointed to the left.
Yeah.
So shouldn't, what's that?
It's perpendicular to the displacement.
Still perpendicular. And what angle would you get in this case? 90, because again, you're not going from 0. You're starting from the displacement and going over to the force. So that's still 90 degrees. It's still perpendicular. That is still entirely correct. Does work of gravity change? Yes. Last problem, gravity did nothing. Let's see if gravity does something now. I think you are right. If you don't know, by the way, even with work normal, even if you're sitting there like, I'm confused how they got that, then go ahead and write out the whole equation. Oops, not normal in this case, gravity. And one of those will probably be 0. All right, what was work of gravity? We didn't use it. Sorry, force of gravity, rather. Force of gravity is 125. Okay, what's displacement? 3 meters. And what should the angle be in this case? 180 is correct. The angle is 180 because we're going from displacement down here. So yep, that will be -1. So your answer should be -375 joules. Lastly, will work of friction change? No. Force is exactly the same. Displacement is exactly the same. And even though friction changed direction, so did the displacement. And what's the angle between the two of them? Also 180. All right, I'm going to ask you the exact same question I did at the end of the last one. Should this box be speeding up or slowing down in this case, or staying the same? Should be slowing down. What is the energy reason why? Correct. And if you want to translate that over to forces, last chapter, once again, we could just look at the y-axis. The only force going up is my push in this. And I said it was 100 newtons at about 86%, so there's 86 newtons in change pushing upward. The gravity alone is 125, which means this thing is definitely going to be accelerating which way? Downward. And if it's going up, but accelerating downward, what's that box doing? It's going to be slowing down until it starts to travel down. By the way, this force diagram will change once it travels down. How? Force friction will change direction, correct. Yeah, well, and also, you're right, but we don't usually draw displacement for a force diagram. All right, so this brings me to, going back to this original equation, there is technically a second equation that is very important to get down here that we've actually arguably already been using, and it is this. The equation for work net. Work net just means the total work. Technically speaking, I could also say this. What does that little guy there mean? Sum of works. The reason I use work net is the following. If you see sum of forces, hopefully you know forces are a vector. So how do you have to add vectors? Vector addition. Okay? Work is a scalar. So how do you add them? Addition. Actually, normal addition that you're used to, 2 + 4 is 6, is a scalar addition. So these are the same thing, these top two. I typically use this one sort of to kind of remind myself that it's not a vector. Meaning, how would I add the works in this case? It's simple. It's the work of 1 plus the work of 2 plus the work of, you know what, let me be more specific. In our example, it would have been the work of person on box plus the work of normal plus the work of gravity plus the work of friction. And that's what we did with each of the previous 2 examples to get the answer of what's happening to the overall energy. Is the overall energy increasing, decreasing, or like in my very first example, walking across the front of the room, staying exactly the same? All right, I got one more example, then I'll be done. Again, we're going to use the exact same things. Here's the situation. Now we're going to go up a hill. Here's my box on the hill. I am once again going to, I'm supposed to put that in blue. I am once again going to put my force on this, but I'm going to put it going up the hill. Here's force of PB. Help me with the rest of the force diagram real quick so we can finish up real quick. What do we got? Gravity down. Normal, which way? Perpendicular. And which way? Yep, we're going to say that in this case that we don't know necessarily what's going to happen. Let's assume that the box is in fact sliding up the hill right now. All right, let's see how this changes. Switching colors to neon freaking green. All right, work of person on box. Does it change? If you don't know, ask the questions that I have been individually. Does the force of person on box change? No. Has the displacement changed? No. Still going to push it 3 meters. Has the angle changed? Yes. It is not 60 like it was originally. It is not 30 like it was a minute ago. What angle is it at? It's weird to look at this. I'm sorry. I apologize. I got to give you one more. You should have known that anyway, but I was also going to tell you that the angle of this hill is 30 degrees. But even though it is 30 degrees, why is that not the angle here?
Because it's going the same direction as the
It's going the exact same direction as the displacement, so what should the angle be? 0. The angle's 0, the cosine of the angle is 1. So that means the overall work being done here is positive 300 joules. And once again, I ask the question, doesn't it make sense? Why does it make sense that I'm putting even more energy in than the last two? Well, now it's perfectly the exact direction it's going, so we should add in the most energy. Should work of normal change? Absolutely not. Even though, once again, it changed direction, because you said it a second ago. Which way was force normal to the hill? Perpendicular. Since it's going along the hill, yeah, that's why it's going to be 0. You'll find that trend a lot for force normal. By the way, force normal isn't always going to be 0. Just a heads up, let me give you a demonstration of when force normal will not be 0. What pushed me up in the air there? Force normal. Force normal pushed me up. This can go up, so force normal is not always 0, but oftentimes it is. All right, so work normal is to say I'm skipping work of gravity for a reason. Is work of friction any different? Is it still the same force? Still the same displacement? Still the same angle? So it should be same angle, yes. It should be at 180 to displacement. Finally, does work of gravity change? Yes, it should, because even though force of gravity didn't change and displacement didn't change, what did change? The angle. What should the angle in this particular instance be? Let me ask you this. Do you see that it needs to be here? Okay. Do this following thing and it'll help you out. Write, even if you don't need them, in your horizontals. Because now you should hopefully be able to get this. What is the angle between vertical and horizontal? From the vertical to the horizontal is 90 degrees. And here's horizontal. Here's horizontal. How much angle is there? 30. So what should the angle be in that case? 120 degrees.
Oh, I see.
That is going to give you a negative number. As a matter of fact, it's going to give you negative 1/2. Does it make sense that gravity, in this instance, should be taking energy out of the box?
Yeah.
Hopefully, yes. Yeah, this should end up being half of whatever negative 375 is. There you go. Negative 150, negative 172.5. All right, that's it.